Okay, welcome back everyone. In this video we're going to be looking at an example problem. This is actually number 41 on page 756. And in this example problem, this is with a concave mirror, and we're given a magnification of positive 3.0, and we're also told that an object is located at 50 centimeters, and that's also positive. So we know that it's concave, and we are asked to find the type of image formed and its orientation. So when we say image type, we mean virtual or real, and we also want the location. Okay, so what we need to do for this, and we also need to find the radius of curvature. So those are the two parts. What we need to do for this is take the information that we have, and I've already written down here that this is DO, which is basically 50 centimeters. And another thing that we can do with the magnification is that this is equal to the height of the image over the height of the object, or negative image distance over object distance. Now, image height and object height, we have no information, so we can't use that, but we do have the object distance, so we can simply write that d image is negative 3.0 d object, so that's negative 150 centimeters. So a negative image location means that it's behind the mirror, so I'm going to kind of mark off what looks like DI. Okay, and DI is going to be right here. Now, we also know that the magnification is 3. Okay, so if I say, for example, that the object has a height of almost 2 lines, then the image is going to have a height of pretty much 6. So that's a magnification of 3 times. Okay, so what kind of image is it? Well, it's behind the mirror, and it's right side up, so it's got to be an inverted image. Where is it at? Well, it's at negative 150 centimeters. And what's the radius r? Well, before we do that, I think that we should do some ray tracing to kind of show you how it's possible that this is actually true, that it's behind the mirror. But it turns out that at the very least we have to find the focus. Okay, so 1 over f equals 1 over do plus 1 over di. Now we've seen this a couple times. So 1 over f equals 1 over 50 plus negative 1 over 150. So this means that 1 over f is equal to 2 over 150, or f is equal to 75 centimeters. Okay, so if I divide DO into 2, that's approximately 25 centimeters. So that means that this point right here is f, because DO is 50. Alright, so now let's try to use some of the principal rays. Principal ray number 1 is, if you recall, a ray that starts at the object and goes parallel to the optic axis. So there's the optic axis. Here's a ray that starts at the object and it comes in parallel. Okay, problem. Can't go through the mirror. So what is it supposed to do? Well, it's supposed to reflect back through the focus. Okay? And like we've done in the past, when we know that we have a virtual image, then we have to extend the reflected ray backwards. And so I do that in this case, and look how perfectly that lines up. Okay, so there's one. Now, what about for the second principal ray? This is the one where the ray is supposed to go through the focus, right? Well, if I were to do that, I would have major issues, because this would just go through the focus forever. And it turns out that we don't actually draw it like that. What we do is we end up drawing it, whoops, okay, we draw it starting at the focus, and then hitting the tip of the object. Okay, and now it's probably not 100% accurate because in this diagram, when you get out at the edges of the mirror, kind of funky things happen, but you get the idea. This is going to reflect back parallel to the optic axis, so kind of like so, pretty close to that, and then we simply extend this reflected ray backwards. I told you it's not going to be perfect. It should have been right here. Okay, so we were a little bit off. Okay, if you look at it, it seems that my original ray probably should have gone more like this, but you get the idea. This is why it's very important to draw this as accurately as possible. Okay, well, what about for the third ray, the ray that goes through the center? Well, where is the center? It turns out it's twice the focus. So if the focus is here, maybe the center is approximately here. I'm eyeballing. Okay, and let me get a different color. Okay, so it goes through the center, kind of like, whoops, let me try that again. I'll start at the center. Okay, and goes kind of like that. And then this ray reflects back, so it goes back through the center, but I can also extend the reflected ray back, and you can see that that one's a little bit better. But again, this is how we ray trace, and we see that the rays converge on the other side of the mirror, because on the real side they are diverging. Okay, so once again, remember that for a concave mirror, that you're going to get a virtual image when the object distance is less than the focal length. This is going to be a virtual image. Okay? Oh, by the way, what happens when the object is at the focus? That's a good question. What if DO is equal to F? Okay, well, that means that I have 1 over F equals 1 over DO plus 1 over DI, and I can substitute, so I have 1 over DO equals 1 over DO plus 1 over DI. Okay, well, those are going to cancel out, and I'm going to get 0 is equal to 1 over DI, which suggests that DI is infinity. And this is actually used in a couple of different applications. For telescopes, it's basically the reverse of this. Okay, for a telescope, you have starlight, which is basically coming in parallel because a star is basically an infinite distance away as far as a telescope mirror is concerned, and all these rays come in and they all bounce and go right through the focus. And I can't draw, but you get the idea. Okay, now the opposite of this is in your car. If you were to put a little light right at the focus, well, then all the light rays that came out of it would bounce off of a concave mirror and go out parallel. So sometime look at your headlights and you will actually see the concave mirror. Okay, so that's it for now, and next time we'll start talking about lenses.